Okay, so today we're going to be talking about inverse functions, but there's no way to really talk about inverses before we talk about, without talking about one-to-one functions. Okay, so we're going to do a little bit of a review back from module one. We're going to talk about what the formal definition of a function is. We're going to kind of review how can we identify whether we're looking at a function or whether a graph that we're shown is a function or not. And then we're going to talk about what is this one-to-one function. It's a special type of function that has a few more conditions that we're going to place on the definition of general functions, okay? So we're going to kind of zoom into something a little bit more specific, and we need to understand that only one-to-one functions can have what we're going to call inverse functions. And so we could think about this PowerPoint as being split into two parts, one-to-one functions and then inverse functions. So let's go ahead and begin with some review. Okay, so you guys have seen this slide before back in module one when we first introduced the idea of a function. And throughout the semester, mostly we've been using a function as an equation where we take some x values, something that's an input, plug them into the function, do some math or plug some stuff into our calculator, and then we get our y values that we call our output values. Okay. We've thrown some vocabulary at you guys and said that the set of all of the x values is called the domain of the function, whereas the set of all of the y values is called the range of the function, okay? But a function is just a type of relation in which each element of the domain, each x value, okay, is mapped to exactly one element in the range. So each x value only has one y value. Sometimes we phrase this and say that y is a function of x, but you should be able to look at a set of ordered pairs or even a graphic like we have here on the slide and ask ourselves, is this a function? So if you vaguely recall that when we first introduced this idea, I had a set of elements that we called the domain, X, and that was a set of names, Bert, Maddie, Lisa, DeAndre, Esmeralda. And then we had a set of health conditions, Y, healthy, diabetic, anemic, and tachycardic. And then there are some arrows connecting them together. So this is technically a set of ordered pairs because if we think about the X values and their connections to the Y values, we can set up or write down some ordered pairs like Bert, comma, Bert is tachycardic, right? So Bert tachycardic is Bert, comma, tachycardic. And just to help myself out, I'm just going to stop at tachy. Okay, Bert is tachycardic. That's our first ordered pair. Are you guys okay with that?
Yes, sir. Oh,
Okay.
sorry.
No, you're fine. You're fine. No
Texas
worries.
habit. Okay.
Okay. So the thing that makes this a function is that if we look at every single x value here, they only have one arrow connecting them to an element in the range, connecting them to a one y value. Okay. So here the definition for function only restricts the behavior of the x values. It says nothing about what the y values can do. So if you recall my very strange and maybe comical analogy that I used, that in the definition for a function, if we think about the x values as being the husbands, then the y values are their wives. Okay. And so for this to satisfy the definition of a function, the husbands must only have one wife, but we don't care what the wives are doing. So this is still a function, even though both Bert and, let's see, DeAndre are both tachycardic. But if we just focus on the behavior of the quote unquote husbands, Bert only has one wife and DeAndre only has one wife, and that's all we're paying attention to. So that's what makes this a function. Any questions about that example? Okay. Really should be a quick review, right? Because then we had some examples when we introduced this concept where I said, here's a graph. How can we tell whether that graph of a relation satisfies the definition of a function? And that's where we applied the vertical line test, where we said, if I can draw any vertical line anywhere on the graph, if I only have one intersection, well, then we can say that that's a function. But if I can draw a vertical line and I have two intersection points, then that's not going to be a function. So we see here with the vertical line that was already drawn on the graph, it intersects the graph at two places. The new one that I drew over here also has two intersection points. And anywhere I draw a vertical line, and let's pretend that that was a straight line, if I have more than one intersection, then that's not a function. Okay. So what we can say is that like these vertical lines represent x values. Like this one over here is representing x equals 2 because this vertical line crosses the x-axis at 2, right? So the vertical line test is essentially a way of visualizing whether the husbands, the x values, have more than one wife. Okay. Any questions about the vertical line test? Do you guys remember this?
Yes, sir.
Yes.
Okay. Easy stuff. Okay. Now we're going to get into the formal definition of a one-to-one function because now we can sort of specify some more restrictions on our functions. So the definition of a one-to-one function that's presented in most math textbooks and that you might see in the ALEKS explanations say something like this. A function f is a one-to-one function if for a and b in the domain of f, one of these conditions is met. And these basically these conditions I'm about to read mean the same thing. They're just two ways of looking at it. Okay, so first, if a and b are elements in the domain of f, and if a is not equal to b, then that implies f of a is not equal to f of b. Okay? Alternatively, another way of thinking about it is that if I have f of a and that's equal to f of b, then that implies that a and b are equal to each other or they're the same number. Okay. Now, this is one of those things where if you were to be teaching yourself math by like reading a textbook and trying to make sense of this on your own, the first time that you read this, it doesn't make any sense. We kind of have to draw a picture for this to make sense, okay? So for the definition, it says A and B are in the domain of F. Okay, so imagine that I have a function and I have a circle here that's going to represent my domain, my X values. A and B are just numbers that are in my domain, okay? And if A is not equal to B, that just means that those two numbers are different numbers. Does that make sense? A and B are not equal to each other, so they're different numbers. We have two different numbers in the domain of our function. Okay, so if we have two different numbers in the domain of our function, then when we map them to the range, we usually take this number, whatever it is, and plug it into the function f of x, right? And so if we do that, we would get f of a, which is essentially a y value or an element in the range. So if I plug in a into the function, I would get f of a, whatever that happens to be. Doesn't really matter what that is, okay? And if I plug the number b, which is a different number, into the function, then I would get a different y value once I calculate or evaluate what f of b is. And so this definition is saying, well, if A and B are not the same, then their Y values cannot be the same. So f of A cannot be the same as f of B. Okay? So that's kind of like a fancy way of saying if we have these two husbands and the husbands are not the same person, and yet they're married to something in the range, then those wives have to be different wives for this to be a one-to-one function. Okay. So here we're finally getting this idea that for us to have a one-to-one function, the husbands must have exactly one wife, and the wives need to be faithful to that one husband. They cannot share multiple husbands. So we are restricting both the behavior of the husbands and the wives for one-to-one functions. Does that make a little bit more sense? Or are there any questions or comments? Going to take a strategic sip of water, see if there's any questions. Okay. So think about it this way, like we have this general overview of functions, but now we're going to focus our studies to a type of function which is more specific and has that additional restriction that not only must the husbands be faithful to their wives, but the wives must be in turn faithful to their husbands. Okay. So I like to say that using that analogy, a one-to-one function is like perfect monogamy where there is no stepping out, there is no cheating. We must have that faithfulness between our X and our Y values. Okay. So if I give you a set of ordered pairs, you should be able to sort of go through the process and ask yourself, is this one, is it a function? And then two, does it meet the requirements for a one-to-one function? So we're going to do this example together. Okay. If I think about all of my X values, or if I ask you to list the domain of this ordered set of ordered pairs, what are all the values in my domain?
1, 2, -2.
1, 2, and -2. That's the domain of this relation X, okay? Because we don't know whether it's a function yet, okay? What's the range of this relation?
4, 3, 4.
4 and 3.
So if we have repetition, we don't have to repeat it. So we have 4 and 3, and you don't have to say 4 again. So it's just 4 and 3. That's the range of this relation F, okay? Then using our ordered pairs, we can draw a connection between the elements in the domain and the elements in the range. So 1 is mapped to 4, 2 is mapped to 3, -2 is mapped to 4. So I'm asking you two separate questions here. First, is this a function?
No.
No, because they need even pairs.
Incorrect. Okay. Remember, the general definition of a function says that the elements of the domain, the X values, need to have at least one Y value. I'm sorry,
Okay.
at most one Y value, or exactly one Y value, actually. And so if I look at this guy, how many Y values does it have?
One.
Just one. How many Y values does this guy have?
1,
How many Y values does this guy have?
1.
Okay. So if each of my husbands only has one wife, then that satisfies the definition of a function. So you have to distinguish these two ideas in your head. In general, you can be a function as long as all of the husbands have one wife. Okay. We don't care what the wives are doing. The only time we care what the wives are doing or what the Y values are doing is when I ask you the follow-up question, yes, this is a function, but does it meet the requirements to be called a one-to-one function? Okay.
No.
So
No.
it's not a one-to-one function because the one-to-one function has that additional requirement that not only do the husbands only have one wife, but now the wives must have only one husband. And this wife right here has two
Wow.
husbands. Does that make sense?
Scandalous.
Yeah. Any questions or comments there on this one? So this one is a function, but it's not a one-to-one function. Okay. So let's look at another practice problem. See if we can, get the hang of this. It's another simple relation here. I have a set of ordered pairs. So can you guys tell me what is the domain of this relation G?
-3,
-3, 1, and 2.
-3, 1, and 2 is the domain. Can you tell me what the range is?
4, -1, 0.
4, -1, and 0, right? So if you needed to, you could draw these little maps, these little bubbles that contain all the elements in your domain and all the elements in your range. Okay. And then you could even use the ordered pairs to draw arrows connecting the ordered pairs, sort of the x values to their partner y values, right? So -3 maps to 4, 1 maps to -1, 2 maps to 0. So I'm going to ask you two questions again. First, is this a function?
Yes.
Yes.
Yes, it is, because all of the x values only have one arrow connecting them to exactly one element in the range, right? So then we can follow up and ask, well, this is a function, but is it a one-to-one function?
Yes.
Yes. So this one is a one-to-one function because the wives or the y values only have one x value as their partner, right? We have no sharing of y values. Does that make sense? Questions, comments? Okay. So I feel like, maybe it should be said that like when you get into the homework, you're going to see some problems that ask you about one-to-one functions. And it's going to be something like this, where if you have a set of ordered pairs, you should be able to say, okay, well, let me look at all the ordered pairs, maybe draw one of these little mappings where I have my domain and my range, and I draw arrows connecting the x values and the y values, right? If you can figure out, whether it's a function and whether it's a one-to-one function, then you're understanding exactly what you need to be understanding at this point, okay? It should not be more complicated than this, at least for these kinds of questions. So this is a function and it is a one-to-one function. Questions, comments before I move on to the next slide? Okay. So this slide basically sums up that the definition that you're going to get if you're reading the ebook or if you're looking at the view example in ALEKS is going to be very formal, because like the language of mathematics, once we get to a certain point in talking about functions, becomes very much like if you were taking a logic course. And if you've ever had sort of the misfortune of taking a philosophy or a logic course, then there's a lot of statements that are made, and you have to figure out if the conclusions are valid, and there's a set of rules that you have to follow. And then the sort of the definitions that you read are very kind of condensed, and they have a lot of symbols that are hard to make sense of unless somebody's actually like paraphrasing it for you. So whenever you see this definition of one-to-one function, I want you to remind yourself that that analogy where each husband must have exactly one wife, that's going to be very helpful, because now for these one-to-one functions, we can think of them as happy marriages, right? Where the husbands are faithful to their one wife and the one wife is perfectly happy and faithful to their one husband. And we should not be sharing wives or husbands. It's not like a lawless land where everybody's sharing their wives and husbands. Um, it's that perfect monogamy. Does that make sense?
Yes.
Okay. Now, all jokes aside, these analogies are supposed to be fun because, like, in my personal education, like, I've taken some anthropology classes and I studied like the social dynamics of chimpanzees and stuff like that, other primates that are related to us. And it is not the case if you haven't like read up on other cultures or traveled to other countries. It's not the case that in every culture throughout time that like monogamy has been the only game in town as far as how human males and females organize themselves, right? So for me, this is like really easy to understand that functions are one thing, but then one-to-one functions are sort of what we think of as common here in the United States or in the Western world. Okay, so I think one-to-one functions should feel natural in a way that maybe functions were confusing because you wanted to force that perfect monogamy and that perfect like faithfulness between the X and the Y partners before. Okay, but now we finally have it with one-to-one function. Okay. So you're going to be given some problems that say, here's a graph. Determine whether the function is one-to-one. Okay. So for now, I'm just telling you this graph is a function. This is a polynomial function. You guys have seen things like this in the previous section. We know by definition that a one-to-one function, or sorry, that we have a one-to-one function as long as none of the y values are shared among the x values. In other words, the wives cannot be having more than one husband. Okay. So can anybody think of maybe a tool or something that we can do to tell just by looking at this graph to see if that condition is met?
Horizontal line.
Yeah. So in the past, when we tried to determine whether a function was, whether a graph was a function, we used a vertical line test. But now we can use a horizontal line test to determine whether or not those y values or those wives are being faithful to their husbands, if you want to continue thinking about it. The more I say it, the more I feel icky, though, because it kind of feels sexist. But hopefully it helps you guys remember. And I guess that's really what's important here. So like this horizontal line that I just threw on the PowerPoint represents the y value y equals 3. And so that wife, if we continue with that analogy, intersects this graph at 2 locations, here and here. Are you guys okay with that?
Yes.
If I trace these lines straight down to the x-axis, then this point here is 2, 3. And this point over here on the left, if I trace this all the way down, is the point -2, 3. Okay? Where the wife, y equals 3, has 2 different husbands, +2 and -2. But based on the definition that I've kind of like been beating into the ground here, that's not going to be allowed for our one-to-one functions, okay? So we can use this new tool, a horizontal line test, to see if our functions are one-to-one, okay? So one thing that you could do is sort of if you're looking at the homework here, and I think you guys can see this pen, you can just turn your pen or your writing utensil horizontally and use it to scan the graph, like move it up and down the graph. And if that pen horizontally intersects your graph at more than one location, then it fails the horizontal line test and is not a one-to-one function, right? So you can imagine it just by sort of taking this yellow line that's on the PowerPoint slide here and just scanning the graph, right? If we scan in different locations, at the top, you can already see we have 2 intersection points. But even if we were to scan further down the graph, down here we have 1, 2, 3, 4 intersection points. Again, really violating this idea of a one-to-one function. So this is why this particular graph fails the one-to-one horizontal line test. Okay, so here's some practice. Look at the graph below And I want you to do two things. First, apply the vertical line test and tell me if this graph is a function. And you can put that in the chat, or you can unmute yourself and just scream it out to all your friends here in the Zoom. Is this a function?
Yes.
Yeah. I'm going to draw some vertical lines here. Each of these vertical lines that I'm putting down on the graph only intersects the graph at one location, right? I'm going to go ahead and bubble them in a little bit bigger here. One intersection, one intersection, one intersection, one intersection. So sure enough, this is a function. And we always want to make sure that we're dealing with a function before we go on to ask the question of whether it's one-to-one. Okay. So this passes the vertical line test. Okay, so that's the first thing we always need to get out of the way. Then we can ask ourselves, is this function, now that we know it's a function, is it a one-to-one function? Does it pass the horizontal line test? And not a rhetorical question, wasn't sure if anybody gave their answer or their response yet. Is this a one-to-one function?
Yes, it is.
Okay, yeah, absolutely. I draw a horizontal line here, 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 and basically anywhere along the graph. And those horizontal lines only intersect at one location. So sure enough, that is a one-to-one function, okay? And in the PowerPoint, I kind of use this yellow line to sort of skim or scan that graph. And by applying the horizontal line test, we can say safely, this is a one-to-one function. Questions, comments there? Okay, practice number 2. Remember, always determine whether it's a function first, and then determine whether it's a one-to-one function. Okay, so is this graph here a function?
No.
No, right? Again, when we're talking about just determining whether it's a function, we're using the horizontal line test. And at multiple locations where I draw a vertical line, I have more than one intersection point for each of these vertical lines. That means that this fails the vertical line test and it's not a function. Okay, well, if it's not a function, it can't be a one-to-one function because it wasn't a function to begin with. So you will see a question in ALEKS that asks you to determine whether a graph is a function or not, and you have to watch out because I think one of the sort of iterations of that question does give you the option of just saying, like, is this a one-to-one function? And if you only apply the horizontal line test, then you're going to say to yourself, like, oh, this seems to pass the horizontal line test because every horizontal line I draw only gives me one intersection with the graph, right? But just because it passes the horizontal line test doesn't mean that it's a one-to-one function. It must pass both the vertical line test and the horizontal line test for it to be a one-to-one function. Any questions there? Okay, so here, just be very careful not to simply apply the horizontal line test. We really want to do our due diligence and make sure that it's a function before we go throwing the horizontal line test at our graphs, okay? So you may, in ALEKS, find one of these problems that it's not a function, and if it's not a function, it can't be a one-to-one function, okay? And I think I have this slide duplicated for some reason. Okay. So here, I think, before we proceed with this next example of one-to-one functions, you at the moment we have one-to-one functions. If we're just looking at a set of ordered pairs, we can see, do the husbands have one wife, and are the wives faithful to their husbands? Okay, so that's one way of checking. Now, if we're given a graph, we now have a horizontal line test that we can apply. And there is one other way that you can tell whether an equation or a function is one-to-one. And so you may run into this type of question in ALEKS. And this is going to rely on that formal definition, which is why I put it on this slide, which says a function f is one-to-one provided that for a and b in the domain of f, if we have f of a is equal to f of b, then a must be equal to b. Okay. And this is going to seem kind of convoluted, but I think I want to walk you through, guys, a couple of examples here to make this make a little bit of sense. So you're going to be given an equation, something like n of x is equal to 2x minus 7. And the way you're going to want to check to see whether or not this is one-to-one is by writing some stuff down on paper. So we're switching over to the document camera. Okay. So this guy is our function. And what we want to do is check to see if it is one-to-one.
Mr. Aguilar, it looks blurry.
It's not focused.
There we go. Okay. So the definition says for a one-to-one function, if you have f of a set equal to f of b, then that implies that a is equal to b. And there's a very simple set of steps that you can take to use this definition to determine whether this is a one-to-one function, even without looking at the graph. So just purely by doing some algebra. So you're always going to start off with this f of a equals f of b statement. Okay, so we're going to start with this guy. I'm going to put 1 here. But our function isn't called f of x. Ours is called n of x. So if you don't mind, I'm going to write this as n of a is equal to n of b. Okay. Now just follow me on this example, and we'll try to make sense of it here in a second and look at another example after this, okay? N of a is giving me a set of instructions. It is telling me take the x value, a, and plug it into the original function, n of x. So we're going to plug n of a into the function, which means I'm just going to take this part over here, the 2x, but now I'm going to replace the x with an a. 2a minus 7 is equal to, well, this one says n of b, which means we're going to take x equals b and plug that into the function. So again, I'm going to just take this like it's a number, like we've done in the past, and just replace the x here. So I'm going to have 2b minus 7 on this side of the equation, 2b minus 7. Okay. So I'm going to give you guys a moment to write that down. This is always going to be the first step of applying this definition of a one-to-one function, because the definition just says if I can set up f of a is equal to f of b, like I did here, then that should imply that a is equal to b. So what I'm going to see, I'm going to try to see if this will work, is if I can use some algebra to cancel some stuff out so that all I have left over in this equation is A equals B. Okay, and if I can do that, then we can say that this is a one-to-one function. Okay, so here we have 2A minus 7 equals 2B minus 7. And let's focus on just getting the A by itself. Okay, so I'm just going to say focus on the A. If I wanted to get the A by itself, how would I cancel out this negative 7?
+7.
Yeah, I'm just going to add 7 to both sides of the equation. But I have negative 7 plus 7. We know that cancels out. And I also have a negative 7 plus 7 over here that will cancel out. So what I'm left with is 2A is equal to 2B. Are you guys okay with that? Well, I want to get A is equal to B. So if we're trying to get the A by itself, how do I get rid of the 2? How do I cancel that out?
Divide.
Divide by 2. The 2's cancel here because 2 divided by 2 is 1. We have A is equal to. And then over here, the 2's cancel out also. And so I get A is equal to B. So because I was able to get from n of A equals n of B all the way to A equals B, this satisfies the definition of a one-to-one function. So what we can say is that the function that we started off with, n of x, is 1 to 1. Questions, comments, concerns?
So we only focus on the A. We don't like do anything with the B.
Well, it's not so much that we only have to focus on the A. That was just kind of my guidance to make it a little bit easier for you guys. Because I think that if you're looking, when students are looking at both sides of the equation, I think it's easy to get overwhelmed. So I think as long as we can get the A by itself by canceling some stuff out, if we can also get the B by itself as a consequence of that, then we can go ahead and say that this is a one-to-one function. Okay.
Thank
So
you.
let's do another example just so that we can make sense of this, okay? Because another question or comment that I always hear whenever I cover this idea in this class is that a student will often say, well, this kind of feels like a dumb game that we're playing. It kind of feels like, well, if I set up f of A is equal to f of B, won't that always lead me to A equals B? And that's not true, okay? So I want to give you guys two different examples to kind of see where it is true, which we've seen already one example, but I think that two examples will be better. And then we'll see another example where it's not true, okay? So let's say that I gave you the function h of x is equal to, let's go with 4x to the third power plus 5. And we're going to go through the same process here by starting off with h of A is equal to h of B, where you can think of A and B are just what we call in the business dummy variables, because they just represent two numbers, okay? So if we set up h of A is equal to h of B, then we'll have two sides of our equation, right? H of A will be 4a to the third power plus 5. Are you guys okay with that? Okay, seeing some thumbs up. Then h of B is just plugging B into this equation here. So I'm going to put 4b to the third power plus 5 on this side of the equation. Okay, so that's my first step. That's how I start this off every single time. Now, we should be able to do some very simple algebra moves to cancel some stuff out. So this is where, Vincent, I was just saying, like, let's focus on the A so that we're not focusing on everything all at once. We just want to focus on one thing. Okay. So like if I'm trying to get the A by itself, right now it has a bunch of stuff around it, right? It has the plus 5, it has the times 4, and it has this exponent of 3. Let's cancel out the easy stuff first, like cancel out this plus 5. So what do I need to do to cancel out this 5?
Subtract 5 to both sides.
Yeah, I'm going to subtract 5 from both sides of the equation. And plus 5 and negative 5 will cancel out. Same thing over here. Positive 5 and negative 5 will cancel out. So what I'm going to be left with is this simpler equation. 4a to the third power is equal to 4b to the third power. And then exponents are a little bit tricky. So we want to like cancel out the 4 before we even try to take out those exponents. So how can I cancel out this 4?
You would divide 4 both sides.
Yeah, I'm just going to divide by 4 on both sides so that the 4's cancel out on both sides. So now I have a to the third power is equal to b to the third power. And then this one might be a little bit trickier, but you guys should, like in the deep recesses of your brain, remember, how do we cancel out a third power?
You take the cube root.
Take the cube root. So I'm going to apply the cube root of both sides here. Cube root, cube root. And the cube root cancels out the third power. So I have a is equal to, cube root cancels out the third power, and I have b by itself. So was I able to get to a equals b?
Yes.
Well,
Yes.
sure. Yeah, and that's exactly what we were trying to do. So now we can say this function h of x that we had is 1-to-1 because starting from h of a equals h of b, we were able to get to a equals b, and that satisfies the definition of a 1-to-1 function. Did that make a little bit more sense going through it the second time?
Yes, thank you.
Any other questions, comments out there? Okay. So I'm sure you guys want to see an example where we don't have this one-to-one function, or we don't satisfy the definition. So I'm going to make up another function. Let's call it f of x is equal to 3x to the second power. Let's go with plus. What did I add last time? I added a 5. Let's add a 4 this time. And we're going to start this the same way. We're checking to see if f of x is 1-to-1. Okay, so we start off the same way by saying if f of a is equal to f of b, then what we should be getting at the end of this is a is equal to b. And if we get a is equal to b, then this is a 1-to-1 function. Okay. So first, f of a is just 3a squared plus 4. And then f of b is 3b squared plus 4. Questions, comments up to this point? So that's going to be our start. And we'll see how this goes. So just to make it easy on ourselves, we want to focus on getting the a by itself. Okay, so let's take care of the easy stuff first, like the addition and subtraction. Can I move that positive 4 over to the other side? Can I cancel it out? How am I going to do that? Yeah, I'm going to subtract 4 from both sides. And positive and negative 4 cancel out here. Positive and negative 4 cancel out here. So now I'm going to be left with, I maybe put my equal sign too high. 3a squared is equal to 3b squared. Okay. Now how do I cancel out 3?
Divide 3.
Divide by 3. Do you guys see how boring this feels?
A squared equal B squared.
Is equal to b squared. And then we have to be careful here. Can you guys tell me how do we cancel out the second power or the square?
Take the square root.
Yeah. Take the square root of both sides. So if we do that, we're technically applying the square root property. Just like when we solved quadratic equations, right? Which it turns out this is a quadratic equation. If you look at the original equation, 3x squared plus 4, quadratic, okay? So when I take the square of both sides, I'm going to cancel out the squares. And now I'm going to have a is equal to, well, I usually write something here when I use the square root property. Does anybody know what I'm hinting at?
Plus or
Plus or
minus.
minus, yeah.
Plus or minus. Okay. So I need that plus or minus because what we just did was apply the square root property. And now I can say the square root cancels out the square, and I'm going to have b here. So like any quadratic equation, I should have 2 solutions here, but really those solutions can be written as a is equal to positive b, which is what we wanted. A is equal to b. But we're also getting a is equal to negative b, which is not what we wanted. Okay. So really, we have 2 solutions here, and we can't really have that because if you think about like the a as being an x value, well, it kind of has, it's attached to this value b, but it's also attached to this value negative b. And that's not allowed for one-to-one functions for a single x value to be attached to 2 y values, if you want to think about it that way. Okay.
You repeat that? About the 2 values not being attached.
So what I'm saying here is that we would have to get a equals b for both of these equations for this to be a one-to-one. But because this one did not give me a equals b, it gave me a equals negative b, right away we can say this is not a one-to-one function. Does that make sense? Okay. Well, then another way that you could have thought about this from the very beginning without even applying this definition is this is a quadratic function. Quadratic functions look like this, right? We call them parabolas. Does a parabola pass the horizontal line test? So right away, if we had acknowledged that this was a quadratic function from the beginning, then this does not pass the horizontal line test. And so that means the same thing, that we're not dealing with a one-to-one function because we would have had 2 intersection points if you graphed this. Okay. Questions, comments about that example? Okay. For the most part, I think if you run into that question, you could just go through these mechanical steps that we kind of went through for these last 3 examples, and you should be able to determine whether or not the function is one-to-one. And it should be pretty straightforward. So don't let, if it seems kind of like all over the place, don't let it confuse you too much, because you'll see once you get into the homework that it probably won't be as crazy as maybe it seems right now. Okay. Okay. And then also, if you download the PowerPoint and then go through the actual viewing the PowerPoint slideshow, then you'll see I run through the steps for how to process this, where we set up n of a and n of b, and then try to solve that a little bit at a time to get a is equal to b. Okay. So that's going to bring us into our discussion of inverse functions. Okay. Does anybody have any questions about one-to-one functions before we begin talking about inverses? You guys ready for this? Is this a ready or not situation? Okay. So I kind of think that the easiest way to think about inverse functions in this class is if we think of a more real world example of where we use functions all the time. Okay. So it's going to be a very simple example that we're going to talk through here. But imagine for a moment that you're taking a trip to Mexico. Okay. And let's say that you've never really traveled to Mexico, although I know a lot of us are from Texas. We're from a very Hispanic community here in San Antonio, so maybe we have ties to Mexico or other Latin American countries. Okay. But for this example, let's pretend we've never traveled to Mexico before, and we know we have US dollars here. That's the currency that we use stateside, but we need to convert that to Mexican pesos before we go over to Mexico, because otherwise we won't be able to buy anything, right? So we're going to go to the bank. We're going to say, okay, I have X number of dollars in USD. That's United States dollars, okay? And the bank has this function in their computer that says, if I get X amount of dollars, I'm going to give the customer, right, the bank goer, 20 times X pesos, right? This was the exchange rate for US dollars to pesos about a few months back when I updated this PowerPoint. Okay, but exchange rates change from month to month, and so it might be a little bit more, it might be a little bit less now. But when I made this PowerPoint, 1 US dollar got you 20 pesos. Are you guys okay with that idea?
Yes.
Okay. So it should be a really natural thing to say to myself, like if I go to the bank and I only exchange $1 American, then the bank's going to give me 20 Mexican pesos. If I exchange $2, multiply that by 20, and I get 40 Mexican pesos. $3 gives me 60 pesos, and $4 gives me 80 pesos. Are you guys okay with that?
Mhm.
Very, very straightforward. Now, presuming that you go to Mexico and maybe you go to an area where it's very safe and there is no cartel violence and you're not getting abducted, you plan to come back from vacation. And when you come back to the States, well, maybe you keep some pesos just for keepsake, but most of the time you'll go back to the bank and say, well, I can't really go to the QT and buy a Dr. Pepper with these pesos. Can I have these exchanged back for dollars? So we want a function that is not only going to exchange my dollars for pesos, but that's going to take my pesos and transport them back into the world of US dollars. Does that make sense? It's a very simple idea, I think. Okay. So what an inverse function is, it's a function that will reverse the operation of some other function. Okay. So when we introduce this idea of inverses, we're first going to talk about some original function, like this function that converts our dollars to pesos. But then the inverse function will reverse that operation, taking our pesos and converting them back into dollars. Okay. And there's a lot of times when you would need a function, a set of functions like this in mathematics. If you ever think about like astronomers, which unless you're a big dork like me, you probably hardly ever think about astronomers. But when they count the number of galaxies and stars that are in the universe, it's something of the order of like billions and hundreds of billions of stars. Those are really big numbers. And so they use certain types of functions, like a type of function called a logarithmic function, to make those really huge numbers become really small and more manageable numbers. And then when they need to convert back, they have a function that takes those logarithms and reverses them or undoes them so that we can get back into the number of actual stars or number of actual galaxies that they counted. Okay. So in science, in mathematics, we like this idea of basically having a function that does something, but then a different function that'll take us back into the original units, the same way we would like to get back to our original currency of American dollars. Okay. So for a moment, if we think about this currency function, we said that we have some values in the domain of our function and some values in the range of our function. So our function is going to take all of our dollars from the domain and compute them by multiplying them by 20 and getting the number of pesos. Okay. So if this function multiplies our dollars by 20 to give us pesos, how can we get our pesos back to dollars? Can you guys think of what
Division.
operation? What was that?
Division
Division. But specifically division by what?
by 20.
Yeah, literally just dividing by 20. Right? So we could think about this simple inverse function as just taking our x, which we're going to call our pesos now, dividing that by 20, and then that'll transport us back into the world of US dollars. Does that make sense? Well, hopefully it does. This should be a very simple toy example. Not all the examples you're going to see in this class are this simple, but that's the main idea here. Okay. So for simple equations, we can think about how to reverse the operation of the original function, and that can help us build its inverse. So you guys understood that multiplying by 20 and dividing by 20 are opposites of each other, and so that's why we know the inverse is division by 20. Okay, but you guys have been using these ideas to solve all kinds of equations throughout the semester. Like when I had in the previous example, 3x squared plus 4. You guys know that if in my function I have a plus 4, to reverse that operation or to cancel it out, I need to subtract 4 because addition and subtraction are inverses of each other, right? The same time when I had a coefficient of 3 in front of the a squared, you guys said, oh, divide by 3 because a coefficient is multiplication and the opposite of that is division. So throughout the entire 8-week course, 5 weeks really, we've been doing these things where we cancel out or reverse operations to solve equations. And really, we've been using inverses but not calling them that. Okay. So we're going to look at some properties of these inverse functions whenever we have them. And these will be very useful properties that will help you answer some of the questions you're going to see in ALEKS. So first, if we think about our exchange rate tables, our first table had x values and y values. So I'm going to label these as x and y just so that it's a little bit clearer. Obviously, this column here of US dollars is x. And then our function here is the same thing as our y values, right? So we have an x column and a y column, and that's our function that we're going to call f of x, our original function. Okay. To get the inverse function table, all you need to do is switch the order of your x and y. Okay, so what I'm literally going to do is just switch the position of my x and my y column, like so. So now, and I'm going to use a different color here, this is my new x value column, but in reality, they were the y values from my original function, right? And then if I look at this column over here, which is typically my y values, originally those numbers came from the x column from the original function. Okay, so if you have a table of an original function, then f inverse of x, which is kind of written as f with a little -1 exponent, parentheses x, we say that's f inverse of x. All we're doing is switching the x and the y values. Okay? So if I have the ordered pair 1 comma 20, and that belongs to my original function f of x, then that means that my inverse function contains the ordered pair 20 comma 1 by definition. Okay? So that's the first property, that if you have an ordered pair for the original function, let's say we have an xy pair, well, that's how we call them usually, xy, in the original function. I'm going to put OG here for original gangster, right? Original function. Then all you need to do is switch that to y comma x. And then that new point that you have will belong to the inverse. Okay? So what you'll notice is if you switch the points, the x and the y values, for every single point, then that's the same thing as taking the domain over here. So this is the domain of the function f of x. And if we swap all the xy pairs, then the domain becomes the range of the inverse function. So this becomes the range of f inverse of x. And also, if I switched all the ordered pairs around, then the y values here, which was the range of the original function, so this is the range of f of x, then that swaps over and becomes the domain of the inverse. F inverse of x. Okay. Now, I know that in terms of like vocabulary, you're getting like a lot thrown at you. You're kind of drinking from the fire hydrant right now. But it's a very simple idea that if I gave you a set of ordered pairs and I asked you to give me the inverse function for that set of ordered pairs, then you just swap the x and the y value. So let's do like maybe a really quick example on pencil and paper so we can see how this looks. So let's say I gave you a function, let's call it j of x is equal to the set of ordered pairs. Let's go with 1 comma 1 and 2 comma 1/2 and 3 comma 1/3 and 4 comma 1/4. A very simple function with just 4 ordered pairs. Okay. And I'm just going to say this is a 1-to-1 function. If I asked you to write the inverse function, and we'll label that as j with this little exponent -1 of x, we read that as j inverse of x. Then what you would do is just say, oh, j inverse of x is equal to, and all I'm going to do is swap the position of the x and the y values. So it's not going to look very fancy for this first ordered pair, because if I swap the 1 and the 1, I get 1 comma 1. Okay? But for the second ordered pair in the inverse function, what should this new ordered pair be?
Should be 1/2, comma 2.
1/2 comma 2. That's it. We're just switching the x and the y values. So like I said, if we have x comma y in the original function, then that means that y comma x is going to belong to the inverse function. So we can now swap this ordered pair. And so what's the next ordered pair that I should have in my inverse function?
1/3, comma 3.
1/3, comma 3. And then the last one should be what?
1/4, 4.
1/4, comma 4. Is that crazy?
No.
Mhm.
Okay. Then we have nothing to be worried about then, right? It's a very simple idea. That's the first property of inverse functions. And so like even if I didn't tell you like that these are inverses of each other, if I just said, are these inverses of each other, then one way that you could check is say, are the x and the y values essentially flip-flopped? And if they are, for every single ordered pair, then that satisfies the definition of an inverse function. And this one's a little bit trickier just because they're both ones, but I think it makes the point. You guys okay with that? Any questions, comments? Okay. Well, naturally, that's going to end up giving us some sort of consequences for when we graph both of these functions at the same time. So like in ALEKS, you're going to see some problems that say, here's a graph. And then below, it's going to say, select the correct function that represents its inverse function. Okay. When you graph these two functions at the same time on the same graphing space, what will always happen if they are truly inverse functions is that they will be symmetrical across a perfect diagonal line. Okay, so this diagonal line that we have here, sometimes we just put it as a dashed line. This is called the identity function. You guys saw it when we introduced some functions at the very beginning of the semester, and the function is y equals x. But you can think about this identity function as just producing that perfectly straight diagonal line. Okay. So for our Mexican exchange rate example, we had two functions, right? We said that if we had $1, that we would get 20 pesos, right? So that's 1 comma 20. If I had $2, I would get 40 pesos. So that was 2 comma 40. And so on and so forth, right? We can see these points have been graphed. Okay. So if I get the inverse function and I just switch the xy pairs, so this was x comma y, and if I switch them around, they naturally sort of transport us across this identity function. And it will be like folding the paper in half. Those points will sort of kiss each other or touch each other. Okay. So we have the ordered pair 20 comma 1, 40 comma 2, 60 comma 3, and 80 comma 4. And that's the same thing as swapping those x and y values. Any questions, comments? Okay. So property 2 is a natural consequence of just swapping those xy pairs. If you graph both the function and its inverse at the same time, they're going to appear symmetric across the xy diagonal, the x equals y diagonal, or the y equals x diagonal. Okay. The next property is a little bit convoluted, especially if you're the kind of student that was struggling with these composition functions or composition operations that we did for test 1. Do you guys remember when we did those examples where we said, we're going to take the output of this function and then it's going to become the new input for a different function? I think I used the analogy of doing your laundry.
Sure do.
You guys remember that?
Mm-hmm.
Okay. Well, there's this other property that's kind of sort of useful sometimes when you're looking at inverse functions, and this idea is that if you were to compose an inverse function with the original function, those two functions will cancel each other out. Okay, so I'm going to walk you guys through maybe a very easy example of thinking about this. So let's think about I'm going to start with the number 10, right? I'm going to say that's my x value. Okay, just the number 10. If I told you, okay, take 10, add 5, and then subtract 5, can you guys tell me how would you go about solving this problem if you're in a math class? How would you go about showing your work?
Combine like terms.
Yeah, we combine like terms. So what's the first thing that you would combine?
The 5 and -5.
Oh, you're going to
Or
combine
the
these
5
guys?
and yeah.
Would anybody take the 10 and
I
then
would
add
take
5 first?
Oh
take
yeah,
the
yeah, yeah.
because they're both positive.
Yeah, so like some people say, okay, well, I could do 10 plus 5, then I can get 15, and then I could subtract 5, right? And then that'll get me back to
Hmm.
10. That should make very simple sense, right? But the fast way to do this is using your knowledge of inverses. Inverses cancel out. So if you know that adding 5 and subtracting 5 cancel out, you could have just said, oh, this is just 10. And you didn't have to go through all of this extra work. So computationally, this is just faster to use this idea of inverses. Okay. So that might be example 1. Example 2, maybe a little bit more complicated. If we had 10 plus 7 minus 7, I'm going to multiply that by 3 and then divide it by 3. How would I start this problem off to try to simplify it?
Cancel out the 3s and 7s.
Yeah. So like I know that these common factors will cancel out, or in other words, that multiplying by 3 and dividing by 3 cancel. And then adding 7 and subtracting 7 are inverses. And so I'm left with 10 again, right? So if you recognize that inverses, when you put them together, will cancel each other out, then it kind of makes the work a little bit easier. Okay. So now, maybe the harder example is like, let's say I gave you a function f of x is equal to 20x, and g of x is equal to x over 20. And I asked you to find f composed with g of x. Do you guys remember how to do these problems?
Mm-hmm.
Okay, well, if you don't, the definition of f composed with g of x, right, where that open circle is a new operation that we can use with functions, is that the first thing that you're going to do is g of x. So we're going to put g of x on the inside of f of x, like so. Okay. And I think that when it came to test 1, maybe quite a few of you guys struggled with these. Okay. But what we're going to see is that g of x is just this x over 20 function. I'm going to put x over 20 here. And then I'm going to plug that into f of x. Okay. Well, whenever I have a function and then parentheses or brackets and I have something inside there, then I'm just going to take that thing and replace the x in that function. Okay. So if I'm taking this x over 20 and plugging it into the function f, what that's going to look like is just 20 times, and then we're replacing the x now with x over 20. Okay. But what do I know about multiplying by 20 and dividing by 20?
They'll cancel each other out.
They cancel each other out. And so all I'm left with
Just x.
is x. And so if this is the thing that I started with, right, this x was my original input, and these functions just canceled out and I'm stuck with my original input, then it means that the functions f and g are inverses of each other because they canceled out. They canceled out completely, and all I was left with was x. Okay. Now, are you going to have to do that here in this class? I don't know that you're going to have a homework problem per se that walks you through an example like that. But this is essentially the third property of inverses, which is often taught when we start introducing inverse functions. So if you do run into that problem, I would just review this video, this little section of the video, to see if it makes sense. But the idea here is that if we have two functions and we compose them with each other, or in other words, if we compose the original function with its inverse, that we don't have to do extra work. We can say to ourselves, well, this is the inverse function, and it's going to cancel out with the original function. And so all we're going to have left over is the original thing that we started with. Okay. So like if I had f composed with f inverse of, let's say I plugged in a 5 into that function. Well, I don't have to do plug 5 into the inverse function and then take whatever that is and then plug it into the original function. Not at all. All I know is that the original function and the inverse, because they're opposites of each other, are going to cancel out. And so I'm just going to be left with 5. Does that kind of sort of make sense? This idea is supposed to simplify your lives a little bit. This idea is going to come into play when we get into exponential and logarithmic functions, which are going to be tomorrow's lecture material and the next day's lecture material, because this whole module, module 4, is about these two new types of functions that we're going to learn. And both these functions, exponentials and logarithms, are both one-to-one functions and they're inverses of each other. Okay. So in different contexts, when we start solving equations using these things, you'll see how they'll cancel each other out. Okay. But for now, that's going to have to be kind of a vague mystery until we actually cross that bridge. All right. So we have these three properties that we've covered about inverse functions. The last property is probably the first one that I should have mentioned, and that's only one-to-one functions have inverses. And that's the whole idea of why I had to introduce inverse functions to begin with. Okay. So that's all we really need to cover for today. There's a couple more slides here of finding an inverse or building an inverse, but I don't think that you guys have problems in ALEKS. This is basically some slides that cover material that we used to have in the homework platform, but ever since we switched on to ALEKS, they don't ask these types of questions. So the last slides, if you see them in the PowerPoint, is just like for your your viewing pleasure, just extra stuff in case you want to go over that. I run through some examples of how you would build an inverse function, run through the steps, but again, not really going to cover it because it's not going to be in ALEKS. Okay. If you guys do see that in ALEKS, then I will cover it in class next time, but I think we want to stop right here and give you guys a chance to sort of work on some stuff in the homework. Okay.